As mentioned in the last video, sample space is the set of possible outcomes of an experiment. For example, if you toss two coins, the possible outcomes, if H is heads and T is tails, would be HH, HT, TH, and TT. This sample space of possible outcomes can also be represented as a T diagram. So here is our listed sample space, HH, HT, TH, and TT. And our tree diagram would look this way. A tree diagram is a visual representation of your sample space. In the coins example, the first set of branches would be the result of tossing the first coin. So these two. Either an H or a T. For each of the first results, we have a second set of branches over here. These are the results from tossing the second coin. Both H and T attached to the first branch. If you tossed a heads with the first coin, you could still theoretically get both a heads or a tails with the second coin. The same is true if you tossed a tail the first time, heads or tails with the second coin. If you total up the final column, right here, it will show you that there are 4 potential outcomes to this experiment. The same number of outcomes that are represented if you list them as we did at the beginning of the lesson. Here, HH, HH, HT, HT, TH, TH, and TT. TT. You can do this with any experiment, regardless of how many outcomes each presents individually, as long as each is an independent event. An independent event is when the outcome of one event is not dependent on the outcome of another, or does not affect the result of the others. Events are considered to be independent if and only that happens. For example, the result of a heads or tails on one coin has no bearing on the outcome of tossing the second coin. The outcome of the second toss does not depend on the outcome of the first toss. Here's another example. If we roll a 6-sided die and toss a coin, 2 completely independent events, it is always a good idea to start your tree diagram with the event that has the largest set of outcomes. That way your tree diagram is less cluttered and easier to read. The die has 6 possible outcomes, so let's start with that. So we list our 1, 2, 3, 4, 5, and 6, and then the outcomes of flipping our coin, either heads or tails, off those branches. You can do it the other way with the heads or tails first and then the 6 rolls on this side. But it tends to, if you have more than 2 events, it tends to get very cluttery. So that's why I like to list your biggest set of events first. If you total these all up, you get your total events, or your total outcomes, I should say. So you have 12 outcomes, and the listed sample space would be 1H, 2H, 3H, 4H, 5H, 6H, and so on. And you can see that displayed nicely in your tree diagram. If you look at the resulting sample space made by the tree diagram and the sample space made by listing the combinations, you can see that the tree diagram is much easier to read and make conclusions about your data. For example, if you are asked what is the possibility that you will roll an even number with a coin toss of heads, you can quickly look to find that answer. Which of these 2 sample spaces do you think would give you the best and quickest answer? You can also make a tree diagram for an experiment with more than just 2 events. If you had to get lunch at the cafeteria and had an option of either a sandwich, soup, or hot dog as an entree, juice or milk for a drink, and cookie, ice cream, pudding, or cake for dessert, you could find all of the combinations of lunch in a tree diagram. So if we take a look at this one. So for this example, I did not start with the biggest one, which would be your desserts. I started with your entree, drink, and dessert, the same way that it was listed in the question. So here I have your sandwich. The branches off of those are either juice or milk, and then from your juice or milk, you can have cookie, pudding, ice cream, or cake. So you do that with all of them, creating all of your branches all the way down. using this tree diagram, what are the total combinations of lunch items that you could get at the cafeteria on this particular day? You can also use a different form of tree diagram to find the probability of meeting a goal represented by a percentage. For example, if you were walking along a path, let's say this path right here, you have 100% probability of walking along this path because it's the only way you can go. If the path splits into two, you have 50% chance of choosing either one of those paths. Whichever you chose now had a 50% probability to walk along it. Let's say we chose the bottom path, this one down here. So we went from 100% probability on this path to a 50% probability on this path. If this path then divides into three separate paths, then you would have to divide the 50% probability by 3 in order to find the percent probability to walk on any of these paths. In this case, 50% divided by 3 is 16.7% each. Let's say at the end of one path is the goal you want to reach. Using the above example, let's say that the goal is at the end of the top of the third path, so right here. We still have one path unexplored that had a 50% chance that you could have taken it. Let's move along that path for a moment and find that it also splits into two more equal paths. Again, we divide our 50% by 2, and then we now have a 25% chance of choosing either of these two paths. If your goal is this pot of gold and you had a 16.7% chance of hitting it along this path and a 25% chance of hitting it along this path, in the whole probability scenario, the way you figure out what the probability of being able to pick or find the right path to get you to this pot of gold, you need to add these two together. So 25 plus 16.7 to give you a 41.7% chance of finding your pot of gold. So that's tree diagrams. Please create a tree diagram on your own that incorporates the possible outcomes of tossing 3 coins.